Welcome back to the deep dive. So if you're a programmer, you know the fundamentals of Python. You're already fluent in the core vocabulary.
Yeah, things like type, int,
Yeah.
print,
Hey,
they're your daily tools.
Exactly. You have the tools, but today we're looking past the basics. We're looking for, I guess, an instant acceleration. We're doing a deep dive into the powerful and I think often really overlooked built-in functions.
Right, the ones that are just there, always available, zero imports needed.
And they act like these optimized primitives that can just, simplify really complex coding tasks.
Yeah.
So our mission today is to find those hidden levers, the ones that take you from being a competent coder to, well, a truly efficient Python master.
I like that.
Okay, let's unpack this.
And if we connect this to the bigger picture, mastering these built-ins is really the ultimate efficiency hack.
A hack, yeah.
You don't just learn a new trick. You learn the most optimized way the Python interpreter is, designed to handle a common task. We're moving from solving problems with maybe multiple lines of code to a single, fast, zero-dependency function call.
Let's start where all computation really begins. Numbers. We live in a base 10 world, pretty much, but when you're working with computers, especially in certain areas...
Like networking or cryptography?
Right, or even low-level systems, you need to be able to quickly visualize a number in a different base. And for this, we have instant converters. So say you have the number 10 and you need its binary representation. You just use bin 10.
And boom.
Python just instantly converts that integer into a binary string, and it's always prefixed with 0b.
And that prefix is key. Because it instantly tells you what you're looking at. For larger numbers, especially when you're dealing with, say, color codes or memory addressing.
Oh, yeah, hex codes.
Hexadecimal is essential. So you use hex, and you get the lowercase hexadecimal string prefixed with 0x.
And just to round it out, for maybe historical or more esoteric uses, you also have octa-x.
Right, which gives you the octal string prefixed with 0o. It's just an instant tool set for that cross-base communication.
It's not just about base conversions, though. It's about bridging different representations of data.
Exactly. And what's fascinating here is the relationship between the human-readable characters we see on the screen and the numerical data the computer is actually storing.
The Unicode code point.
The Unicode code point. We read the letter A, but a computer reads the number 65.
Right.
And Python gives you this perfect bridge. It's two functions that are exact inverses of each other, ORD and HR.
Okay.
Think of it like a character phone book. If you give ORD a character, like ORD A, it looks up the number and gives you the integer code point, 65.
So it's looking up the number for the symbol.
Precisely.
Yeah.
And conversely, if you give R that integer in SAP45, it gives you the string character back.
So if you're building a tool that needs to check if a character is, say, a capital letter, you don't need a huge list of A, B, C, D.
No, not at all.
You just check if it's or values between 65 and 90. That's a powerful bit of utility, especially for parsing or even light encryption. Speaking of raw utility, let's move past encoding and look at what defines the data itself. Everything in Python is an object, right?
Right.
And every object has this unique identifier, like a fundamental fingerprint. How do we actually find that?
We use id_object.
And here's where it gets really interesting, I think. The output of id is a unique integer, and it's guaranteed to be constant for that object's lifetime.
It's basically the memory address, the little neighborhood in memory where that object lives.
Okay.
And this connects directly to a huge concept in Python, immutability. If you write a 5i and then later you write a 6, the number 5 didn't change.
Right, the number 5 is still 5 somewhere.
Exactly. Python didn't update the object at its original ID. It just pointed the name to a new object, 6, which lives at a completely different unique ID.
But wait a minute, if id is tracking unique memory addresses, isn't Python smart enough to reuse memory for really common things? Like the number 1 or an empty tuple?
That is a fantastic probing question.
It just seems like that would mess up the whole unique ID idea.
And you've just hit on something called object interning. For very small integers, usually from max of 5 to 256, and sometimes for short strings, Python does pre-allocate and reuse them to save memory.
Ah, I see.
So if two variables point to the number 5, they often will share the same id. But for larger, dynamically created objects like a big list you make at runtime, the id is guaranteed to be unique until it's garbage collected. It shows you how much optimization is happening behind the scenes.
And that optimization is exactly what we're looking for. Speaking of optimizing, say high school math homework, let's talk about div mod.
This is a perfect example of a shortcut. Normally, if you need the result of a division and the remainder, you'd run two different operations.
Yeah, AB for the division and a paper C for the remainder. 2 steps.
But dibmod AB does both in one shot. It returns a tuple, and that tuple has both the quotient and the remainder.
So it's just cleaner code?
It's more than that. The key insight is that the Python interpreter often translates that single function into a single, highly optimized bytecode operation. So it's significantly faster than running the two operations separately.
So it's not just cleaner, it's actually faster.
Faster code. And while we're on math, let's not forget POW, base exponent. Yeah. It's another one that handles powers much more efficiently than just using the double asterisk operator, especially for very large numbers.
Now we get to, I think, the core structure of a running program. If we want to understand what names and variables are actually available at any given moment, we need to look at the symbol tables.
Right. Symbol tables are basically dictionaries. They're what Python uses to manage all the names, your variables, your functions, your classes. They map the name you use, like my variable, to the actual object ID we just talked about.
And we have 2 of them to look at.
We have globals and locals. Got globals. Returns a dictionary of the current global symbol table. So everything defined at the top level of your script.
Okay, the big picture.
The big picture. Locals, on the other hand, gives you a dictionary of names available just within your current scope. So like inside the function you're currently running.
But why do I need to see these dictionaries? Can I just print my variables?
This is where the practical power comes in.
Yeah.
Imagine you're writing a logging function, or maybe you need to programmatically access a variable, but you only know its name as a string at runtime.
Right, maybe you read it from a config file or something.
Exactly. You can't just write print my variable name string. But you can inspect the dictionary from locals, check if that string name exists as a key, and then pull out its value dynamically.
Wow.
These functions are indispensable for introspection and what's called metaprogramming.
That's a huge shift in perspective, moving from just using variables to actively manipulating the environment where those variables live.
And that's the perfect lead-in to the one we have to talk about, the one that's, well, it's incredibly powerful.
And incredibly dangerous if you're not careful. We must address eval.
Ah, the double-edged sword.
Absolutely. This function gives your program the ability to execute code that's just contained in a simple string. The argument is literally parsed and evaluated as a Python expression.
So if you pass it eval 582, it just gives you back 20.
Exactly. Or if you pass it a string that calls a function you've defined, it just runs the function. The power here is dynamic execution. But the warning, and it's a big one, is that if an external user can feed input into your eval function,
they can potentially run malicious code on your system. It demands extreme care.
So this raises an important question. Why does it even exist? When should a developer risk using it?
Well, we see it used a lot in certain controlled environments, like competitive programming. On online judge systems like Cadis, there's a classic problem on there called buka. It's a math task. You read 3 inputs that form a calculation, like 4, then V and 2.
And you have to solve it.
Right. And if you tried to parse that logic yourself, you'd spend, 15 minutes writing if statements.
Yeah.
The official hint for that problem is to just join the 3 input strings together.
And then run eval on the result.
And then run eval.
Yeah.
It's the designed shortcut for certain high-speed computational problems.
That really shows the intent, doesn't it? The language designers put these tools in for maximum efficiency, even if they come with a big warning label.
Precisely.
All right, let's round out our utility toolkit before we wrap up. Let's focus on the essential workhorses that save us effort every single day. We've all needed to find the biggest or smallest number in a list.
And for that, you have max, you have the min, returns the largest item in an iterable. And an iterable is just anything you can loop over, like a list or a tuple.
And it can also just take a few arguments directly, right? Max, 10, 25.
Exactly.
Yeah.
And min is, of course, the inverse. But often the utility we overlook is how we present the data once we have it. That's where format comes in. Format gives you such precise control over the output. It's crucial for things like financial data. You give it a value and a format specification. So if you need exactly 2 decimal places, you can just use format value, tot2f.
And it handles the rounding and everything for you. No custom string logic needed.
It's all about presentation precision.
And finally, let's revisit our oldest friend in the Python utility belt, the one we all use from day one, print. Even this one hides some complexity.
It does. If you look at its full prototype, it's actually quite long. Print, object, sep, end, file sys.nstat, flushes.
Most people never touch those last arguments.
They don't. But they offer incredible control because it takes object. You can put any number of values. But the two most useful arguments, I think, are sep and end.
The separator and the end character.
Sep defines what goes between the objects. It defaults to a single space.
Yeah.
But if you're printing, say, a comma-separated list, you can just set sep and not worry about adding the commas yourself.
I can't tell you how many times I spent ages debugging output early in my career because I forgot that sep was the default and I had extra spaces in my log files.
Exactly. It's those little details.
Yeah.
And end defines what gets printed at the very end. The default is a new line character, n, which is why every print starts a new line. But if you set end, you can keep printing on the same line.
Which is great for progress bars or something like that.
Incredibly useful.
And that just reinforces the entire point of this deep dive. Mastering Python doesn't always mean writing thousands of lines of complex code.
No.
It means knowing that the combination of these optimized, zero-import built-in tools provides immediate performance solutions to real programming problems.
He's gone from simple number conversions and character codes to defining object identity with id, optimizing math with divmod, inspecting the program's environment with the symbol tables.
And even executing dynamic code with eval.
Right. These specialized functions are that hidden leverage you need to drastically improve your coding efficiency and your foundational understanding of how Python really works.
Now, for something for you to mull over, we learned that globals and locals return dictionaries of all the variables available. The keys are the variable names, the values are their contents. We also talked about the powerful but dangerous eval. So, if you can access these dictionaries that define the entire environment where your program is running, and you can also execute arbitrary code, how could you programmatically inspect or even modify that environment? Could you, say, define a variable using eval and then immediately see it pop up in the locals dictionary? We'll challenge you to explore what happens when you use eval together with the symbol table functions. That is a deep dive for another day.